Right now, every message you send is protected by a lock. Your bank, your email, your government, every encrypted connection on the internet. They all rely on the same mathematical fact: multiplying two enormous prime numbers is easy. Factoring their product back into those primes is impossibly hard. A classical computer, the fastest one ever built, would take 300 trillion years to break that encryption. That is longer than the age of the universe by a factor of 20,000. A quantum computer running a specific algorithm could do it in hours. That machine doesn't fully exist yet. But every major government, every intelligence agency, every major tech company knows it's coming. This is not science fiction. This is the most consequential engineering race of the 21st century. Classical computers are extraordinary machines. In the last 60 years, they went from filling a room to fitting in your pocket and became roughly 1 trillion times more powerful. But they have a fundamental constraint. They think in bits. Every piece of information is a 0 or a 1. Every calculation is a sequence of yes or no decisions, made one step at a time. To check whether a number divides evenly into another, a classical computer checks one candidate, then the next, then the next. Sequentially. One at a time. Quantum computers don't work this way. They exploit two phenomena you've already seen in this series: superposition, from the measurement episode, and entanglement, from last week. This episode is where those ideas stop being philosophy and start being engineering. For classical bits can check one of 16 states at a time. For entangled qubits hold all 16 states simultaneously. At 300 qubits all entangled, you hold more simultaneous states than there are atoms in the observable universe. So what is a qubit, physically? It's any quantum two-state system. An electron's spin up or down. A photon's polarization, horizontal or vertical. The current direction in a superconducting loop. Before measurement, it exists in superposition. Mathematically, the state is written as alpha times the 0 state, plus beta times the 1 state. Where the square of alpha gives the probability of measuring 0, and the square of beta gives the probability of measuring 1. They must add to exactly 1. The universe enforces this. A Hadamard gate, one of the basic quantum logic gates, takes a definite state and puts it into perfect superposition. Equal probability of 0 or 1. Now add entanglement. A CNOT gate, controlled knot, entangles two qubits into what's called a Bell state. The system is now described by one joint wave function. Measure one, and the other is instantly determined. This is where the exponential power comes from. 10 qubits, 1,000 simultaneous states. 50 qubits, 1 quadrillion. 300 qubits, more states than atoms in the observable universe. And a quantum computation operates on all of them at once. But there is a catch. A crucial one. Here is what most popular explanations get wrong. A quantum computer doesn't simply try all answers at once and hand you the right one. When you measure a quantum system in superposition, it collapses to one answer. Just one. And without careful design, that answer is random. So the question becomes, how do you engineer the superposition so that the right answer is overwhelmingly likely when you measure? The answer is quantum interference. You design the algorithm so that quantum probability amplitudes, which can be positive or negative, like waves, interfere destructively for wrong answers and constructively for the right one. Before measurement, the wrong answers cancel themselves out. The correct answer amplifies. This is called amplitude amplification. It is the core mathematical trick behind every quantum algorithm. A quantum computer isn't a faster classical computer. It's a fundamentally different kind of machine, one that uses wave mechanics to navigate a solution space in a way that has no classical equivalent. Two algorithms that define what quantum computers will actually do. First, Shor's algorithm. the one that breaks RSA. RSA encryption works because factoring is hard. Given the product of two large primes, finding those primes takes exponential time. Classically, the time grows faster than any polynomial as the number gets larger. Shor's algorithm exploits a mathematical pattern hidden inside the factoring problem. The function a to the x, modulo n, for any base is periodic. It repeats with some period r or find r, and you can factor n. Classically, finding that period is hard. Quantum Fourier transform finds it efficiently because the periodicity appears as a pattern of constructive interference in the quantum state. Classical factoring, time grows exponentially with the size of the number. Shor's algorithm, time grows as the cube of the number of digits. For a 2048-bit RSA key, that difference is the gap between 300 trillion years and a few hours. Second, Grover's algorithm. For searching. Classical search of an unsorted database of n items, you need to check half of them on average. Grover's algorithm finds the answer in roughly the square root of n steps. Not exponential. A quadratic speedup applied to every brute force search problem in existence. Password cracking. Optimization. Protein folding. The speedup touches everything. 3 things you should know about the world we're entering. First, the internet is already changing. In 2024, the National Institute of Standards and Technology finalized 4 post-quantum cryptographic algorithms designed to resist attacks from quantum computers. Every major browser, operating system, and security standard is now migrating to them. This migration needs to be complete before large-scale quantum computers arrive. Second, quantum simulation may be the bigger prize. In 1981, Richard Feynman argued that only a quantum system can efficiently simulate another quantum system. The most important molecules for drug discovery, enzyme active sites, photosynthesis mechanisms, room temperature superconductors, involve quantum effects that classical computers cannot simulate accurately at scale. In 2019, Google's Sycamore processor, 53 superconducting qubits, performed a specific task in 200 seconds. The best classical supercomputer would have needed 10,000 years. IBM's public roadmap targets 100,000 physical qubits by 2033. Third, and most urgent, harvest now, decrypt later. Adversaries are already recording encrypted internet traffic today. Storing it. Waiting for quantum computers powerful enough to decrypt it retroactively. Medical records. State secrets. Financial data. Everything encrypted with current standards is potentially vulnerable, not in the future, but going backward, once the machines arrive. This is why post-quantum cryptography is not a future problem. It is a present one. You've now followed the quantum arc from start to finish. Tunneling. Measurement. Entanglement. Computation. The physics that seemed like philosophy in 1935, that Einstein called spooky, that Bohr called unanswerable, is now being engineered into processors that will reshape cryptography, medicine, and science itself. Next episode, we go somewhere else entirely. The largest objects in the universe, black holes, turn out to be the most quantum objects in existence. Hawking radiation. The black hole information paradox. And the possibility that the universe itself is a kind of quantum computation. Subscribe. New physics every week. The deeper you go, the stranger it gets. See you next week.